Okay, this is the next speaker will be Susanne Schnell, and she's from Northwestern University, and the title is History and Future Direction of Flow Imaging.
Thank you very much. I'm actually now in Germany at the University of Greifswald. I changed a few years back. Thank you very much for this invitation, and I will talk today about the history and future directions of flow imaging, which is also, as you all know, a non-contrast MRI technique. So you have seen probably this picture before. So this is an example from Kelly Jarvis from Northwestern University of a Fontan case that depicts the blood flow in the venous part in blue and in the blood that comes out of the heart in red. So this is just an example to show you for what the flow MRI nowadays is used. The intention is to assess the blood flow and or tissue motion in order to evaluate the regional cardiovascular function, for example. And we can do this because we exploit the sensitivity of the MR signal phase to flow and motion. So we pretty much measure phase shifts of moving spins. And we can do this by the use of bipolar gradients. So how did this come about? It was actually back in 1960 that Irving Hahn had originally this idea, and he formulated this in his paper called Detection of Seawater Motion by Nuclear Precession. So if you have a constant velocity and if you use a constant field gradients, you can measure the velocity as a phase shift. This is what he back then already had formulated. But it took over 20 years for this idea to catch on, to actually starting to realize this. And from then it became actually really quick that the method evolved. So Paul Moran then published this paper called A Flow Velocity Submatographic Interlace for NMR Imaging in Humans. He showed that by the use of a bipolar gradient, you actually could measure flow. However, he didn't try this out yet in a human being. So this was done by Van Dijk about 2 years later, that he actually measured a 2D phase contrast slice of the chest, and this is how his picture looked like. So in the top you see a magnitude picture, and in the bottom row phase picture, and this scan took him about 8 minutes. And he actually had to draw this the anatomy so that people would understand what he would show here. What was interesting, however, is that he said back then that phase contrast could be used in all parts of the body, that this could detect impaired motion of heart walls, that this could potentially quantify heart wall velocities, that we could measure blood flow velocities, that we could determine volume flow, that we potentially can detect obstruction in vessels, or that we could compare left and right side blood flow. And he also mentioned this to be a three-dimensional Fourier transform method. So already back then he thought of all these things that we do nowadays. Then at about the same time came Bryant with his paper where he applied phase contrast difference, the phase contrast difference technique, also by using a spin echo sequence actually. And he then went to validate the sequence. Here you see in this dashed line in the common carotid artery that he validated his results with Doppler ultrasound. And this is how his validation looked like. So he wasn't really doing that well, but it was very encouraging back in the day. So then it took 2 more years until Naylor came around with the first implementation of using a gradient echo sequence. And he suggested that because there was a lot of signal void in the spin echo due to the flowing blood. So this was pretty much the birth of flow imaging, how we do it nowadays, I think. So we use a bipolar gradient that allows us to bring back our static spins to a phase of 0, and our moving spins have a phase offset, as already Hahn suggested, our moving spins have a phase offset that is proportional to our phase. So we do have an unknown background phase, and which is why we do two scans. We measure a reference measurement as well as a flow encoded scan that we subtract. Norbert Palk, however, showed us to go further. In 1991, he showed encoding strategies for 3-directional phase contrast MR imaging and showed us that we can do this in several ways. He also suggested the terms of Wenk and dynamic range. So Wenk is the strength of our flow encoding in our phase contrast sequence. So from then on, we knew that there would be two methods: the flow compensation method, where we bring all of our spins in the reference scan back to 0, and a bipolar gradient that is flow encoded to measure our the second scan for the subtraction. And the other way is to scan 2 flow encoding scans. This saves us a little bit of time, and we then again subtract these images from each other to then be able to calculate our velocities from the phase. So this is where we have been for many years, that we now can acquire a 2D phase contrast slice, for example in the chest, that we can now use to quantify, for example, the cardiac output, regurgitation, valve function, or peak velocity. Interesting enough, though, Philipp Kehner came then in 1993 with the first depiction of velocity vectors. He measured 3-directional flow and showed that you can use this information to draw these vectors into your data. So he could, for the first time, describe patterns in the flow that haven't been seen before. Patterns like this or like this in the aortic root were suddenly visible, and this, I think, was the basis of our particle traces that we have nowadays. However, some things haven't been solved yet. In 1996, Wikström showed how to actually do the temporal resolution of a 3D phase contrast imaging sequence. So he didn't only do 3-directional, but now also 3-dimensional, and he did this in a time-resolved manner. So, however, he already back then said, well, if we had faster gradient systems, we could reduce our scan time or could increase our spatial resolution, or if we use actually other than conventional sampling and trajectories, for example, stack of stars, we could also potentially be much faster in acquiring our scans. So all of these pioneers really early on had visions of how we actually do things nowadays. So he came up with this segmented case-space solution for the temporally resolved acquisition that we probably all use nowadays. And this were his 3D images, again with here down here a vector graph depiction. And then, of course, all of the problems we have with phase contrast MRI, the noise, the eddy currents, the velocity aliasing, the misalignment of the flow displacement, the distortion, all of these problems were described by many pioneers back in the 90s and early 2000s, and also solutions of that were suggested that we are still using nowadays to correct our data. And another big step in the development was actually Michael's paper on how to use navigator-gated 4D flow MRI. And this was a significant step also in 2000, but already now in 2007, to reduce the breathing artifacts. So he suggested to use a navigator that can adapt the gating to increase efficiency. And this were now the images after applying this. So they dramatically improved from this 2D slice that you saw earlier to a now 3D time-resolved depiction and into streamlined visualization. So this is the magnitude and the 3 phase contrast MRI images of a nowadays 4D flow acquisition acquired with respiration control and with 5 to 15 minutes. But how did it come about? Well, we needed the stronger gradient systems. We needed the pulsed array phase calls in order to do parallel imaging. We needed the field strength and so on and on. So all of these steps happened in between, and I'm not mentioning a lot of authors and a lot of papers because I only have 15 minutes. So nowadays we apply 4D flow in many body parts. In the chest, for example, in the brain, in the heart, as well as in the carotid arteries or in the portal vein, and there are many other applications coming out that are very interesting also for the clinical questions that we can answer. A very recent paper that came out in collaboration with Northwestern and Lausanne is now this 5D flow development, where we cannot only resolve the cardiac phases, but also the respiratory phases. I'm not sure if it is clear yet what the respiratory phase will give us as a clinical question, but it is a very interesting area to actually dive into. So what do we do now with all these images? And this was a major part in 4D flow MRI, was actually to develop all of these quantitative parameters and how to derive them. So the first thing, of course, we have to do the pre-processing. As I said, there are a lot of error sources. We can do the visualization and then the quantification. So again, I'm not mentioning a lot of pioneering work here because there was a lot of work done by many authors to derive washer stress, pulse wave velocity, kinetic energy, relative pressure, etc. All of these things were developed mainly in the 2000s and 2010s. But I would like to point out this recent paper by Tekla Oechtering and co-authors, where she looked at repeatability and reproducibility of various 4D flow post-processing software programs. And this is, in my opinion, a very important work, because unfortunately the result, and this is a lot of Plant-Altman plots, the result shows that none of the softwares really agreed. You can see 4 software packages, A, B, C, and D, and they all tried and they were all compared to each other. So even if 2 software packages agreed in some parameters, they completely disagreed in other parameters. And so there is really a large variety. So I think this is the main problem we have to tackle now. So the reproducibility and reliability is what we have to work on. So what is the future? I think we need to work on the image processing, automation. Maybe we have to work more with AI in order to get reliability, to be maybe more independent from the human. And this has been shown in many publications that are coming out now. For example, the segmentation of data sets by Haben Behain or Mariana Bustamante, or to use deep learning for anti-aliasing, here again by Haben Behain, or to use deep learning for background phase error correction. So a lot of developments right now are going into automation. I don't know if this will solve our problems, but it could be. Or we could use AI to increase our spatial resolution, so we potentially can acquire our data much faster with low resolution, and then apply an AI algorithm to increase the spatial resolution or to get to higher quantitative accuracy. And this was shown by Edward Ferdian in the chest as well as in the brain. Or we could actually still work on better algorithms. If we develop algorithms that are not so dependent on sensitive parameters, such as peak velocities, where we know we are very variable in our result. For example, as shown here by David Malevi, he introduced a relative pressure algorithm that is called VVerb. This algorithm does not depend on peak velocity and could be one way to go. So what is most important, in my opinion, and you may have a different opinion. We need a fast, reliable, and reproducible visualization and quantification of actually disease. We need to be able to apply this routinely, so this means that we need to be able to easily extract results without manual work and without long labor time. So the question is, what can we, and this is an open question because I don't have the answer, what can we as developers still do to help bring this method to be more reliable and reproducible? What can we do so that the vendors help us doing this? So 4+D flow imaging allows us to measure the quantitative information about blood flow as well as tissue motion. We can spatially and temporally resolve the blood flow or tissue motion. We can quantify many interesting parameters and visualize the blood flow. We have a lot of challenges that we tackled or tried to tackle in the past. And this is from image artifacts to long acquisition times. I don't say that we solved all of these issues, but we have done big steps to be able to do this measurement much faster. Or to, and I didn't mention this, to increase our dynamic range, or to have higher spatial resolution or SNR. But what we have to really work on, in my opinion, is reliability and reproducibility. And with this, I would like to thank you for listening, and I hope we have a nice discussion later.
Thank you.